Justin, nice to have you with us.
Good
Thanks
to be
very
back.
much for coming.
You bet.
Intel. We've all heard of this company. You know, it's just around. It's in the air. It's kind of fun to, and you have enough time there to look at the sweep. What a story!
Yeah, it is.
And no matter what one thinks of a certain market or a segment or a device or a chip, the story of Intel has got to be maybe the most interesting, dramatic American success story in corporate history, I think. So,
Well, it's up there.
It's right up there.
Yeah.
And certainly ups and downs and challenges. And so we're going to cover some pretty broad territory, I think, today. I'd like to just start by giving you a shot at a general view of when you look out 3 to 5 years forward. How do you feel about things? How does it look to Intel? How does it look to you? Are there areas of great excitement, areas of challenge? What are you seeing?
Sure. Well, you know, this is really, I think, interesting time at almost every level, and you know, it just gets me excited. It gets me to work every morning. There's so much to do. You know, we continue to push Moore's Law. We made this recent announcement about 22 nanometer technology, vertical transistors. That is important in I think ways that go way beyond the actual announcement.
So let's stop for a moment in case.
Okay.
I know what you're talking about.
Sure.
So three-dimensional chips. We're talking about going from 2D to 3D. We're adding some shape to this and getting additional transistors per square inch or whatever, you know, cubic.
Right.
And the result is that this ongoing Moore's Law story of doubling every 2 years or whatever it's supposed to be will continue for a while.
Well, and that's what I think makes 22 nanometers so important, is that it actually opens up a whole new range of opportunities for technology development, for device development, because we've come out of the bulk, which is the 2D world we've lived in, you know, planar technology. It's not called planar for nothing, and now we're going in the third dimension. We're going in Z. And all kinds of things become possible once you do that, not the least of which is a much broader range of material options. So silicon is becoming, you know, if you will, the substrate, on which many other things can be done. And we've already publicly reported on building gallium arsenide transistors on top of silicon, not using SOI, silicon on insulator technology, but using these buffer layers, as we call them, that lets us put down very high quality material. So, okay, so the transistors are changing,
right?
And you know, we went for 40 years with a silicon gate transistor. Life was good, and then we got to the point, and these things started to leak.
Yep.
You know, like the dimmer in your dining room, and you know, we had to say, whoa, wait a minute. We went to high-K metal gate, but that was just the first one, and there's actually a whole line of these things that are coming now. So a time of tremendous change and ferment at the you know, semiconductor level.
So we're freer to use different materials. We're not restricted to silicon anymore. We're freer to use different dimensions than we were before.
Right.
We're freer, I think, you haven't said this yet, we're freer to use different assembly techniques than we were before. Is that true?
Yeah.
So it's almost like everyone's seen the 3D printing you know, cover on the technology review. And so we're actually able to use techniques and like 3D printing, right? Like deposition techniques that use guidance from, you tell me.
Well, actually, you know, that's an entire subject unto itself. Is how do you print?
Yeah.
You know, I don't know if many people understand that we actually pattern far below the wavelength of the light that we use to expose the chips when we're doing patterning. I mean, the light source is at 193 nanometers, and yet we're drawing lines that are, you know, 22 nanometers wide. You know, if you had a high school physics class, you probably heard that was impossible, right? You can't pattern below the wavelength.
Yeah.
But in fact, we use massive amounts of computation. We do what's called computational lithography, and some of the biggest computers on the planet that remain largely unknown. They're not listed in the top 500. You know, work 24 hours a day around the clock, computing the masks, really, I think the easiest way to think of it is they pre-distort the image, and then the sort of the defects in the optical path get corrected. It's sort of like noise reduction headphones, you know, sort of anti-noise, and you know, when you mix it together, this goes away. So we actually corrected computational, and now we're starting to use multiple masks as well per layer. So it's become very sophisticated, largely to put off the move to X-ray lithography, which is going to be a massive change for the industry.
Change.
Radical change.
Yeah. And when is that going to happen?
I've never been good at predicting that crossover point, so I won't speculate this morning. But it's years away. It's not going to happen
5 or 10 years.
Yeah. I mean, we've gone to immersion lithography, which means we're wet at 22 nanometers, and that's sort of the latest thing. But sort of necessity being the mother of invention, people keep finding ways to extend conventional lithography.
Right. And I think one of the interesting transitional moments that you're describing is that for so long, you guys and Applied Material, the guys who supply you with machinery, have been very good at not making that change.
Right.
And finding other ways to not have to go through that experience. But we're almost there.
We're almost there, and work continues. I don't walk out of here thinking, well, Justin said X-ray is, decades away. But, but we constantly are reevaluating the costs of making the transition, and sort of the pros and cons of the technologies. And as long as we're able to eke out another generation, that the costs tend to favor sticking with what we've got.
Right, but it's kind of, I sense this excitement about, wow, that was 30 years on that platform, and then when you start a new platform, it's got to be exciting because there's going to be all these new things you can do.
Well, my point is we haven't settled down.
Yeah.
This is a time of tremendous change.
Right.
And that's, we're like back in the 60s. Materials are changing. I mean, we went from silicon gate to high-K metal gate. What the devil is that? And, what does that do for you? And now we're 3D transistors. So I don't think we've stabilized, right? We haven't found that technology platform that's going to carry us for several decades. We're still thinking around, trying to figure out exactly what that new recipe is that they'll have the longevity that we saw in silicon gate.
And when you say you see Moore's law continuing for a while, what's a while?
Oh, well, generally...
the newest a while.
Well, generally we look out about 3 generations. Generations about a 2-year cycle. Okay. I think Gordon Moore, in fact, used to say, hey, generally we can kind of see out about 10 years. Maybe it's not quite 10 years. Maybe it's 6 to 8 years. But that's been a constant horizon.
Yeah.
We always can see, and part of it is that, work's going on right now in the research labs at Intel on what that technology will look like 3 generations from now. So, we're below 10 nanometers. I think 8 nanometers is sort of whatever it is, 2016 or thereabouts. And, and people are hard at work on those technologies. So we have a lot of confidence, out 2 or 3 generations. Beyond that, we've never been able to see further, but we're not worried.
That's how it is.
I guess is the best way to put it.
That's the lab time.
Nobody's staying up at night.
Yeah. Right. Well, different kind of question about competition. When you look around the world, there's probably never been more competition than there is now.
Yeah.
Whether it's ARM, whether it's new kids in China, whether it's going to be somebody from somewhere else. In terms of staying up late, that would be more, my guess would be.
Yes, I would think that's fair.
So some of the pressures aren't just the Moore's law pressures, of course, but pressures for lower energy requirements, heat dissipation, specialization probably, various radio-like things, and wireless chips. So as you look around at the competitive landscape, how does it feel?
Well, as I said, we see all this change at every level, and there's no question that within the last few years, certainly with the advent of smartphones and now the tablets, that the computing landscape is also changing dramatically, and there's probably more uncertainty at that level than there is at the chip level.
Yeah.
Right? That we understand pretty well. We don't have nearly as clear view. But I think the shift for us is from the PC-centric view of the world to what Paul Otellini, Intel CEO, has called the Computing Continuum. Now there's this ever-increasing range of devices that include PCs, but of course phones and tablets and television and automobiles. My wife just got a new BMW, and it has connected apps, and she drops her iPhone in, and all of a sudden, these things start happening in the car. Not all of which we figured out at this point,
right.
But that information environment is just penetrating everything. The internet is everywhere in devices and embedded systems, and so this is really a big change for us. And we made this announcement, I guess, week before last, about one of the biggest roadmap changes ever. And I think that's a reflection, and we can talk more about it if you want. That's a reflection of Intel saying, "Hey, this is not your father's PC. This is a different world."
And that was a reduced energy.
Go
ahead and tell us.
Well, so we, I think it's best to see this in the context of the growing importance of user experience. Certainly, in consumer markets, but I think it certainly extends to enterprise, because we tend to judge the quality of our enterprise technology more and more on the basis of what we experience at home.
Right. I'm going to call this the Steve Jobs effect, if that's okay with you.
Exactly.
Really, and you guys are working with Steve, and it's had a huge effect on.
We certainly do.
So the user delight, user experience.
Yes, absolutely. And so, one of the things that the devices, if I can use that, these internet devices, have done for us is raise our expectation about the quality of the experience, right? So, why shouldn't a laptop run all day? Your phone runs all day. You've got much more room. Can't you put a bigger battery in there? Well, not if you've got a 35-watt processor in there. That's going to drain pretty much everything we have today. I mean, maybe a battery will come along that'll change that. But we're going to, with the announcement, we're going to reset the targets down, from 35 watts to 15 watts. And that will, easily double the battery life. We're going to be much smarter about the way we manage the displays. Most of the time, nothing's happening on your display.
Right.
But the whole platform is running.
Yeah.
And that you can, I demonstrated this at the Intel Developer Forum, 4 or 5 years ago, where I literally unplugged the display from the rest of the notebook, and it kept running. And the whole, we just literally pulled the power out of the notebook. And if you can do that on a, millisecond by millisecond basis, I won't go finer than that, but there's huge amounts of power to be saved, because the platform can go, can either go into a sleep state or a very low power state, and then, when you finally hit a key or click a mouse or touch the screen, it wakes up. You don't see any lag. It just appears to be, fully there. So energy efficiency, things like instant on. I mean, I'm sure everybody in the audience.
Well, we were laughing on the phone when it's like I heard about that in 1945.
Right. Well,
how many Steve Ballmer speeches have I heard that?
And it's interesting how the PC industry really resisted that. There were efforts. I mean, Microsoft had efforts. Intel had efforts.
And all the driver guys wanted to be in the. Yeah, right.
And the industry just couldn't digest it, however you want to describe it. But now, I want to pick up, my notebook, and I just want it to be there. I don't want to sit there while it figures out where it is and why it is. And all
I just
that.
bought a new system. It's already doing that again. It's kind of like I'm up to the 3-minute boot time again.
Yeah, right.
I remember there was, I will not name him, but a friend of mine from Intel, this is 15 years ago, and he said, I can boot that, whatever I had. We have it in the lab. It boots in 15 seconds.
Right.
We know how to do this.
Yep.
And clearly it was not a technical issue as much as it was the pressure from this community to be, well, what about my thing? What about my thing? I got to be part of the boot process, right? And the whole issue of having an open system, which was nice compared to Apple, but at the same time, the cost of that was incredible.
Right.
in lots of ways. So,
And
it
so
seems like we're going back toward the...
Oh, yeah.
Okay.
Yeah, I think a lot of these technologies, if you will, that have been put on the shelf are now coming back to coming back to life. And within the next, literally year or two, I think you're gonna see that the PC experience is going to feel much more like the device experience as in terms of battery life and responsiveness. And
it's being driven by smartphones, by people's experience.
It's the experience.
Of the phone.
Right. It's the
I turn it on, the
phone.
thing's on, right? Why should I have a different experience with anybody? Yeah.
Right.
It strikes me that will require having soldiers standing around the boot sequence, defending those few poor guys in the middle from the rest of the community saying, "I want to be part of that deal."
Well, the technology's gotten a lot better too, and so some of the tricks we can play now. I'm thinking of the growing presence of flash memory in all of these platforms has a lot to do with their ability to wake up quickly. You don't have to suck things off of disk and wait for literally minutes, as you say, before the system comes to life.
So I'll have to buy another computer in a few minutes.
I hope so. Right?
So
pays the airfare.
If we look at the world you just described, and there are all these new devices happening, and all these countries, and it's a rapidly changing, not only competitive, but market landscape for you guys.
Right.
If I were Paul or you, and I'm trying to figure out, well, how do I own that? I would try to create interdependencies for my chip families so that they were not only the best, but that they had something special so that you always wanted mine, right?
Mm-hmm. Right, sure.
You guys working on that?
Yeah, I think it's sort of part of this continuum view. How can we take advantage of a lot of the commonalities, both in a hardware and a software sense, and I guess increasingly in a services sense. I should add that as well, so that as you move from device to device, platform to platform, there's a continuity of experience, and I think that's embodied in things like iTunes, right? I mean, wherever you find Apple, you find iTunes. That's a good example.
But is that a chip-based story?
Well, no, but it's a service that spans all of these devices, and but we have to translate that into hardware and software terms. I mean, what does the middleware look like, and the operating system, and it certainly includes things like the security technology, which which may be one of the key areas in which we're able to add value by guaranteeing, hey, if you're running on Intel, you're going to get the best security we know how to build.
Exactly. Thank you, because that's exactly where I wanted to go next.
Okay.
And so you guys purchased, and I don't even know how to pronounce it, Mcafee?
Mcafee, yes. It's not Mcafee.
Yeah, I keep hearing Mcafee. It's like,
that's okay.
It's Mcafee.
Plenty of Intel people still call it Mcafee. Yeah, so
whatever they're called, Mcafee.
Mcafee, yeah.
All right. And there were some obvious reasons why you might want to do that. But in our conversation, I think it was yesterday, about BIOS and coming down to the metal. And so it strikes me that one obvious way of doing what we were just talking about is providing the security down to the metal so that you can have a device, at least down to the device, what that device is. You might know who owns it. You might know where it's supposed to be. You might know where it is, and all that stuff. So there's a level of security available on booting, which wasn't available before. It was technically around, but it wasn't hooked up, let's say. So, fair enough?
Yeah, okay.
So, in a new version of trusted computing, we might have this operating on any device, right? And is there a synergy to having this happening on an Intel chip? Or is it the fact that there is an Intel chip that will do that gives me the comfort of that's why I want to have that happen?
Well, yeah, I think I guess it's a bit of both. I think we've really shifted our posture on security. I think Paul was on TV over a year ago, and made this statement that security was now sort of the third leg of the stool, behind performance and next to performance and energy efficiency is security, and I think there were plenty of people at Intel that were surprised to hear that as well. Those of us who worked on security, of course, were applauding and cheering, but he really meant it. And Paul, I mean, has been very serious about this, and so we've been hard at work developing security capabilities that will be top to bottom. I mean, that's another part of the mandate, top to bottom in Intel platforms. So, Atoms and, all the low power stuff, the mainstream, PC processors and the servers. And as you were suggesting last night, many of these IP attacks are actually at the server level, not at the, not in the clients. Clients are it's too hard to find it in the clients, with millions of them or billions of them. So people go to the servers because just the sheer number is that much smaller. So one of the things that I think is game changing, at least from a technical point of view, I don't think we can yet say whether the economics of it will present itself, is this notion of zero-day defense.
Yeah.
And now that we're
for those who don't understand what zero-day defense is, a zero-day attack is when you use something which hasn't been exposed yet, and so Microsoft or Intel, whoever provides the hardware and software, have never seen it, and the security companies...
it's more Mcafee and Symantec and that
they have not seen it,
right?
And so there isn't a cure for it yet,
right?
And that's why it's called zero-day. It's the very first day of its exposure,
yeah.
And they're like crown jewels. If you own one and you're a bad guy, you save them for the big hunt.
Well, you don't even have to be. It turns out you don't even have to be that clever. In fact, take Operation Aurora, Project Aurora, the thing that cleaned out the Google servers, and took some things off the Intel servers and a number of other companies. You can change just a few bits, and the signature-based anti-malware software will never see it. It'll just go, oh, that looks good. Go by. Right. Meanwhile, rootkit installed, and all of a sudden, we're in there, as was described last night, munging around. Oh, that's interesting, and finally we find the crown jewels, right, and all of it comes out. So signature-based methods are, 30 years old, and basically what you buy is a service that updates you on the signatures. But again, you can go on the internet, you can find sites, and they'll give you Aurora with a few bits changed, and goes right by. So nothing is thwarting these IP attacks that you were talking about. So we took this is, you talked about getting rid of the frames and taking a fresh look. We sort of threw out all of the assumptions and said, okay, what if we came at this from a fresh perspective? And one of the sort of important things was, what if we sort of took this out of software and put it in hardware? Could we do that? And in fact, that's what led us to this notion of a zero-day defense, which does not rely, tell all your friends, does not rely on signatures, because a lot of, when we first talked about this, a lot of the talking heads were saying, well, there's no way they could put 6 million signatures on a chip. There are no signatures on the chip, and yet we can detect Aurora, we can detect Stuxnet, all of the the well-known ones, and literally we've run millions of attacks against the architecture, and it stops all of them. I don't know. There may be one we haven't seen, but so far we've not missed an attack, and we detect it right at the point of insertion, and within within milliseconds, that can go up to the cloud. I mean, think about having when we start shipping, which is still a few years away, hundreds of millions of ultra-sensitive detectors. I mean, anybody attempting a major attack will be spotted almost instantly up to the cloud, and then the billions of devices that don't have this capability will be informed. So they'll get the signature, if you will, determined on the fly.
Okay, I want to bring us back to Earth here for a minute. What's the name of this stuff, this magic secret sauce?
Just, zero-day defense.
That's enough?
That's enough.
That's not enough, because everyone uses that term for something else. What is the name for it? What can we call this as an Intel technology that will appear in
No, I think I'll just
sometime.
stay with zero-day defense.
Zero-day defense.
Yeah.
Okay, it's hardware-based, zero-day defense.
Right.
And
Top to bottom.
and you said how many years before
A couple
chips?
of years away.
2 years. Okay.
Yep.
I was at a black hat kind of conference in Toronto a few years ago, and I was definitely the idiot in the room. And one guy with a T-shirt that from no company you would, and we were talking, and I said, well, the only way I can see to solve this whole virus thing is if it's like a highway, a toll road, and every time a PC is turned on a network, it has to show who it has to have permission to get on the road. Right. It has to have a driver's license, right? It says, I'm clean, I have no diseases, and I've got the right tools on board so that I won't get sick.
Yeah.
And that way we could make sure. And we'd be like, if you don't have that, it gets stuffed down your throat for free for 3 days, and then you got to pay for it, or whatever it is. And he said, you're not an idiot after all. and which was a great compliment.
Right.
So I feel like that's what you're telling me.
No.
Because if you guys have that, when you turn them on, right?
Well, so this is a different.
I want to have that?
You definitely do. And we talk.
And the network will see me.
That's right.
And it'll know that I've got that stuff on there.
Right. Right.
And if I were smart and I were either Mcafee or Symantec or anybody, I'd write software that would say, first step, recognize those machines.
We have that. This is another thing. The technology is there to do this,
Yeah.
right? We have the identity technologies. We even have the architectures that are more symmetric, I think, than you sort of did it one way. Okay, you're a clean client. We know your identity. You've given us some hash of your OS image, and we know there's nothing bad going on. But how do you trust the server?
Yeah.
So we actually have architectures that insert brokers, and the broker says, okay, you want to talk to that server? Well, prove to me, that you're a trusted identity, right? By the way, I will go talk to the server and make sure, this server's not spoofing,
so
Bank of
exactly
America or Visa.
It's a toll road we're talking
right.
about with a
and
cop.
And then once both ends of the connection
That's
have
the
been
traffic cop doing the toll road.
Well, then they step back. I mean, there's a certificate exchange,
No,
and then the broker's at it.
Yeah.
You don't want the broker arbitrating all this stuff.
No.
Part of the problem, not the entire problem, but one problem I'll highlight this morning is there's sort of two prevailing views of this, and not to be too hard on the network guys, the equipment guys, they have this view that security is port to port. So you come into their router and a switch, and you come out of their router and a switch, and they guarantee nothing bad happened between that port and the in-port and the out-port. I think the computer industry, and include all the device people, really see this as end-to-end security. I mean, it's nice that the port-to-port connection is guaranteed, but we really need to go from client to server, or server to server, or client to client, and we need to authenticate and credential that entire path.
Yeah.
And that's where we're kind of running into a bit of a problem, because in fact talk to the major carriers, right? These people who come from a network heritage. They go, oh, we don't understand these devices. We don't like these devices, so we're making our networks really secure. And you go, well, it matters not. I mean, if the endpoints aren't secure, actually, you're making life easier. You're guaranteeing that nothing bad will happen port to port, and so the guys who are doing bad things at the ends are going, hey, that's great. They won't bother us. We'll just go right through.
Exactly.
So that's a problem.
I keep thinking the box guys are going to teach the pipes guys how to do this.
Yeah, I think. Well,
we only have a minute, but I know we have questions on the floor for
sure.
Justin. So if you have a question, do we have? There's a microphone there. There's a microphone there. Please stand up and ask a question. There we go, right there.
Stephen Sprague from Wave Systems. So could you really articulate this as the beginning of sort of an identity-centric model to computing as opposed to a connection-centric model computing? I think that's the paradigm that needs sort of better explanation. So only subscribers or subscriber devices get access to a service. And it's fundamental, one of the fundamental pieces that is a gap in understanding for everybody is registration. So the process that will change for everyone is how do we register a device with a service so then it knows that it's a device I've seen before.
Right, and I agree. And how do we measure continuously to establish the ongoing integrity of the endpoints? All of that is there. And some of the early attempts to do that, of course, were hit by the privacy folks, and I don't take anything away from the privacy folks. I think they're well motivated, but finding this balance between identity and privacy has proved somewhat elusive, and I think we're moving closer to being able to resolve those issues, and I think anybody who works in this area knows that identity is a foundational element. So I completely agree with that. I think it's just navigating these difficult waters to find the acceptable middle ground between privacy and identity.
And unless we have another person going once, going twice, okay, great, we've been out of time.
Yeah,
Thank you very much.
Enjoyed it.